Okay, so thank you everybody for coming. Welcome to the One World seminar on the mathematics of machine learning. Today's presentation will be given by Alex Safsten, who is a PhD student at Penn State. And he's going to speak today about the stability and accuracy for deep neural network classifiers. Thank you, Alex. The floor is yours.
Thank you, Stefan. Today I'll be presenting work which is joint with my advisor, Dr. Lina Berliant, and Dr. Pierre-Emmanuel Jabin, who are both at Penn State. Today I will be talking about the classification problem in machine learning. So in the classification problem, you have several objects which are represented as points in S from Rn, and each one belongs to one of k classes. And we have a function phi hat, which is an exact classifier, which maps each object in S to its correct class. But the problem is that phi hat is only known on a finite set, which we call the training set from S. And the question is, how can we extend phi hat so that it approximates the true phi hat on all of S? As an example of the classification problem, we could try to find a function that places each picture of a cat or a dog into the class cat or the class dog. And so here's an example of 8 pictures, but of course there are many possible pictures of cats and dogs, and it would be challenging to find a function that would be able to take each one represented as a point in Rn and map it to the class cat or the class dog. The way that this problem is generally solved is using supervised machine learning, and specifically by constructing a soft classifier, which is a function phi depending on parameters alpha, where alpha comes from some other high dimensional space R mu. So phi then would be a function from Rn cross R mu, and it maps to the unit cube of dimension k, of the number of classes. That is, the function phi has one output for each class. And these outputs will sum to 1, so that we can interpret each one of the components of phi as being the probability that the object S belongs to that class. So a phi I of S alpha is the probability that S belongs to class I. And that's what we mean by soft. So deep neural networks are a very broad class of algorithms that have many uses, but in particular, they're very good at solving the classification problem. The deep neural network, or DNN structure, is the composition of rho and x. So x is what we call the logit function, and it is a composition of many other functions. So we write it here as lambda composed with fm, composed with lambda again, composed with fm minus 1, and so on, until one last lambda and then f1. So each fk is an affine function, which depends on many different parameters, such as matrix elements. And these parameters are what make up the multi-parameter alpha. So if we have many large matrices, you can imagine that alpha would indeed be a very, very large collection of parameters. And these parameters will play an important role in the training and the use of deep neural networks. Lambda is a nonlinear activation function. For example, absolute value function, or so-called rectified linear unit, which is the max of 0 and x. Today we will consider only piecewise linear activation functions. There are others, of course, but we will just stick with piecewise linear for today. Together, each composition lambda with fk is a layer, which is a word that is frequently used in connection with deep neural networks, and deep refers to the fact that we have many layers in this composition of x, the logit function. Finally, the last function that is a composition of that is in the composition of the deep neural network is rho, which is a softmax function. And the purpose of the softmax function is simply to normalize the outputs of the logit function so that they are probabilities. So if we denote by I of S the correct class of S, then the goal is to optimize alpha so that each phi sub I of S, that is the component of the deep neural network that is the correct class of S, is approximately 1, placing each object into its correct class with approximately 100% probability. So the question is, how do we optimize alpha? And the main tool that we will use to do that is the loss function. The loss function maps from the parameter space R mu into R measuring the performance of the deep neural network. A typical example of a loss function is the cross entropy loss, which is the weighted average of the log of the correct output for each object in the training set. So that if each object is placed in its correct class with approximately 100% probability, then this weighted average will be a weighted average of numbers that are close to 0, and we will get a very small loss. The weights, nu of s, measure how important or how reliable the classification of each object is. So if we will typically have weights that are approximately uniform, but there's no reason that they have to be uniform, so we'll leave nu of s to be a general probability measure for now. The training process is the process of numerically minimizing the loss function using, for example, gradient descent, but there are many other more sophisticated algorithms based on gradient descent. But the key here is that alpha, the parameters, change in time as we train. So we think of alpha as being a function of time. This leads to the convergence of the training algorithm. So this is the first result. We can convert the discrete training algorithm into a PDE via kinetic approach. Then alpha of t solves the ODE for characteristics, and then we obtain some differential inequalities for this ODE via entropy dissipation. The result is Theorem 1, which establishes tight bounds for loss. That is, loss is bounded both above and below by very similar functions, so that loss goes to 0 in a very controlled way. Second, we also have an upper bound for alpha of t, for the size of the set of parameters. But notice that this upper bound is itself unbounded in time. So it's possible that alpha of t diverges. However, it only diverges as log of t. So it diverges very slowly, and for practical purposes, it converges. A famous quote by De Gennes: "Logarithm is a constant." However, this theorem depends on an important assumption, which is that at some time t naught during the training process, and for all later times, every object in the training set is correctly classified and is placed in its correct class with probability being greater than eta, or greater by eta than any other object. So not only is each object correctly classified, but it is correctly classified by some margin, some fixed margin. So this is a strong condition, and it might be hard to satisfy for some data sets. Furthermore, it has to be verified not only at time t naught at some point during training, but for all later times, which can be difficult to do. And finally, in order to satisfy this condition, it may require many parameters for our neural network, resulting in overfitting the data set, which is never good. So this leads us to the thought that we might relax this condition, leading to questions of stability of accuracy, which is the focus of the rest of the talk. And as a note, there are other notions of stability, some of which have been discussed in this very seminar. And we will just note that stability of accuracy is different from some of those other notions of stability of deep neural networks. So the idea of stability of accuracy is based on this observation that training decreases loss, but it might not increase accuracy. Accuracy is defined as the weights of all of the objects that are correctly classified at time t. As an example of this phenomenon, consider the training set with 50 objects, and each object has equal weight, and there are 2 classes. And so we train for a while, and we arrive at the point where 49 objects are correctly classified with 52% probability of being placed in the correct class. But one object is very badly misclassified with only 1% probability of being placed in its correct class. This means we have 98% accuracy. However, after some later time, all objects are misclassified with 49% probability of being placed in their correct class. Therefore, we have 0% accuracy. However, we can calculate the loss at both times, and we see that loss does decrease. So though loss decreases, accuracy has fallen drastically. This is obviously not a situation we want to see, And so we want to identify conditions that lead to this kind of situation and rule them out. Now, of course, this example, which is constructed artificially, is a bit extreme. But as a more realistic example, we could see instead of one very poorly classified object, we have several objects that are misclassified moderately, and they have about the same moderate misclassification. And this is what we call a small cluster. We will use that term frequently throughout the rest of this talk. So previously we were talking about convergence of the training algorithm. Now we're going to talk about the stability of the training algorithm. And by stability, we will use the following definition. For every epsilon greater than 0, there exists delta greater than 0, such that if accuracy at time t naught is bigger than 1 minus delta, then accuracy at all later times is bigger than 1 minus epsilon. So this is a clear analogy to the notion of Lyapunov stability. And we should note that stability is a dynamic property. I should say stability of accuracy. The type of stability that we are discussing today is a dynamic property, as opposed to other types of stability, also called robustness, which are static properties. And the main use of stability is that it helps us decide when we will be able to stop training, when we can say, okay, our neural network is done, it is trained enough and ready for use. I see we have a comment in chat. Thank you. Do we have any questions? Okay, so I will discuss the tools that we will use to explore stability. The first is classification confidence and its distribution. So for simplicity, for the remainder of this talk, I will assume that we have only two classes. And so for each S in our training set T, we have I of S, which is the true class of S, and we have I star of S, which is the wrong class, the other one. So we'll define classification confidence as delta X, and it's equal to the logit for the correct class minus the logit for the incorrect class. And recall the logit is the output of the neural network before normalization. So the property that delta X has is that if delta X of S is positive, then S is well classified by the DNN. And if delta X is negative, then it's misclassified by the DNN. And the bigger that the absolute value of delta X is, the more confidence the DNN has in either the correct classification or misclassification. So even if it's wrong, the DNN thinks that it's right. It's very confident. And the reason that we like to talk about delta X is that it is easy to use it to calculate both loss and accuracy, as shown in equation 3. We have nice simple formulas for both loss and accuracy using delta X. The other tool that we have to study stability is good and bad sets. So these are generalizations of accuracy. And we define the good set of margin eta at time t to be those objects that have delta X at time t bigger than eta. So not only are they well classified, but they are well classified by a margin of eta. And the bad set are the objects that are misclassified by a margin of negative eta. So delta X is less than negative eta. So nu of g eta of t is the mass of g eta of t, and it measures how much data in t is correctly classified by a margin of eta. And we'll note that that nu of g0 of t is just equal to accuracy. So now we can explore what properties lead to bad stability or lead to instability, and then we can rule those properties out, and then we have stability. So we'll use the term poorly classified objects to mean those objects that have delta X less than eta. So our main question of stability is if we start with some small number of poorly classified objects, then will that number remain small as we train? And the main enemy here will be small clusters of delta X values that are less than eta, especially those near what we'll call beta, the minimum delta X value. So in these pictures, we have on the left a narrow small cluster of red misclassified objects near near beta. And then on the right, we have a wide small cluster. So it's wide in its extent, but it is small in the area beneath the red portion of the curve. And we will find that the narrow small clusters are worse for stability than the wide small clusters, but in general, they are both bad. So the major assumption that we were going to use going forward is that at some point T0 during training, most objects are well classified. That is, nu of G eta is bigger than 1 minus delta for some small delta. And the mass of everything else then would be less than delta. So this means that any cluster that we might consider, any cluster of misclassified objects, must be small because it must be of size less than delta. Hence the term small cluster. We can further explore what properties of the initial data, the training data, lead to small clusters in delta X and are therefore bad for stability. So we'll introduce the term data manifold. This is the manifold that the data points in Rn cluster near. As an example, if we were studying geolocation data on the surface of the Earth, these will be points in 3 dimensions because the Earth is 3-dimensional. However, the surface of the Earth is a 2-dimensional sphere. So the data points would cluster around this spherical manifold as opposed to being a true 3-dimensional data set. So the first point is that a small flat portion of the data manifold M can lead to a small cluster in the set of classification confidence values, delta X's. So the reason for this is that delta X, because we consider piecewise linear activation functions, delta X is itself a piecewise linear function. So this means that if we have a small interval, a small cluster that is contained in a narrow interval, then if we map this cluster back to the space of the data via the delta X map, we obtain a piecewise linear set intersected with M. So therefore, if the data manifold has a small portion of itself that is contained inside of a hyperplane, that is a small portion of it that is flat, then that small flat portion might map forward back to a narrow interval, forming a small cluster. So we want to rule out data manifolds that have small flat pieces to them. So we will call this the linear mechanism for instability. We also have a nonlinear mechanism, and linear and nonlinear here referring to the linear and nonlinear maps that are both compose the DNN. So if we have a large flat portion of M, well, this in the linear sense is not a problem, because a large flat portion of the data manifold would map to the real numbers by a linear map to possibly a large cluster. But this isn't a problem, because remember that we assume that we have only we have only a small number of misclassified objects. So if we see a large cluster, this means that this is a large number of well-classified objects. And so a large flat portion of the data manifold is not inherently a problem. However, this large flat portion could be mapped first, before it ends up in the real numbers. It might be mapped to an intermediate manifold by the activation functions of the neural network, which remember are piecewise linear. And these piecewise linear maps may break the large flat portion of the data manifold into several small flat portions. Consider, for instance, a long flat line that gets broken up by a piecewise linear map into a jagged line with several small flat pieces. So this is another potential source of instability. So we need to rule these sources of instability out by some condition. And the condition that we will use is a doubling condition. So the idea of a doubling condition is that if we have data from some space Rd and a bounded domain W in Rd that contains some of those data points, if we were to expand W in all dimensions, then if the new expanded or doubled domain, which we'll call 2W, contains no more data than the original domain W, then the original domain W must have contained a small cluster. So consider, for instance, the picture on the right. where we have an ellipse which contains some of the green data points, and then we expand to the big ellipse which contains no extra data, we conclude that the small ellipse must have contained a small cluster of data. We would prefer instead to have the situation on the left, where we start with a small ellipse and then increase its size to the big ellipse, and the big ellipse contains a lot more data than the small ellipse did. So mathematically, we obtain this condition in equation 6. So we assert the existence of kappa and sigma greater than 1, so that for all bounded domains W, the number of points in kappa W, the expanded domain, is bigger than the number of points in the small domain by a factor of sigma. So here we'll call kappa the doubling parameter. That's the amount that the domain grows when we quote unquote double it. And sigma is how much bigger the number of points is after we double it. And so we want the number of points in the big domain to be substantially bigger than the number of points in the small domain, so that we do not have a small cluster inside the small domain. So we'll start with our first implementation of the doubling condition. And this is going to be a doubling condition on the classification confidence values. So since the classification confidence values are real numbers, this is a doubling condition in one dimension. So this leads us to equation 7. We will assert that there exist kappa A and sigma A greater than 1 and delta greater than 0, so that the mass of those objects from the training set, so that delta x is inside of the expanded interval kappa I, is bigger than either delta or sigma A times the mass of objects, so that delta x is inside of the smaller interval I. So you can look at the picture below. We have I, and then we have the expanded interval kappa I. And we would like there to be more objects inside the expanded interval than inside the small interval. Now you'll note the presence of delta to be slightly different than the doubling condition on the previous slide, where there was no delta. And the reason for this is that we only want to detect small clusters with this condition. We don't want to detect large, well-classified clusters. So we put this little delta in here so that we don't detect large clusters. Now, I see that we have a question in the chat. The question is W not required to be centered? So going back to the previous slide, we have the small ellipse W, and then it is quote unquote doubled to the bigger ellipse. And so we will, when we make the transformation from W to 2W, we will change the dimensions of W, expanding it in all dimensions, but leaving its center of mass the same. This, of course, requires some formality if W is not a very well-behaved domain, such as an ellipse or a rectangle or something. But you will see that in the end, we will consider only well-behaved domains, so this will not be an issue. And then, of course, asked differently, does the doubling condition have to hold for all W? As stated, yes, for all bounded open W in RD. This is, of course, a very strong condition because there are a lot of open and bounded sets. So you'll see later that we will restrict ourselves to a smaller class of sets. Of course, when we consider the doubling condition in condition A, this is in the real numbers. And of course, the bounded open sets in the real numbers are a little bit nicer. And if we say, and we are going to further restrict ourselves to only intervals. So the doubling condition A becomes rather simple because we only consider intervals. However, condition A can be strengthened, leading us to a new condition, which we'll call rather uncreatively condition B. And this is a stronger doubling condition on the set of delta x values. So the idea is that all of the masses, the mass of any number of objects that is nu of any set is less than or equal to 1 because nu is a probability measure. So if we raise the size of the bigger interval in the doubling condition to a power bigger than 1, then we decrease the size of the bigger interval, or rather we decrease that side of the inequality. And this makes the inequality sharper and therefore stronger. So we can rule out more small clusters this way. So the result, therefore, is we say that that the mass of objects delta x, mass of objects s, so that delta x of s is less than beta plus gamma over 2, is less than or equal to k times the mass of objects, so that delta x is less than beta plus gamma to the power of psi. So psi decreases a little bit the right-hand side, making the inequality sharper. In fact, it might mean that the right-hand side, without this k, it might mean that the mass on the right-hand side raised to the power of psi is less than the mass on the left-hand side, even though the interval is bigger because of the power of psi. So it might be necessary for k to be bigger than 1. And the more concentrated the cluster, the bigger k must be, and therefore the worse for stability. So in these pictures at the bottom, we have the picture on the left with a narrow interval for which we would need a very large k, and the picture on the right with a very wide interval, a very wide cluster, which would require a much smaller k. Now, the faster this delta x distribution decays to 0 at beta, the larger we can let this exponent psi be, and bigger psi leads to a better stability result.
Can I briefly ask a question?
Certainly.
You're talking about the data points. Do you need that the data is discrete, or could you just send the number of data points to infinity and basically have a continuous distribution?
The condition as stated actually works better for an infinite number of data points. If we consider very, very narrow intervals, it's possible that we contain maybe only one data point in this interval, in which case maybe that one data point by itself would be counted as a small cluster. And this, of course, is not desirable, because at its heart, every data point would be counted as a small cluster, and we don't like that. We want to count only small clusters on a scale of many data points. So in order to account for a discrete set of data, we actually need to modify equation 8 slightly. We left it as is for the purposes of this presentation, but in the paper you can see the more detailed condition. So the answer to your question is that, in fact, this condition would actually, the condition as stated, in fact, works better for a continuous distribution of data than a discrete set of data.
Thank you.
Mm-hmm. The final condition that we will discuss, which we call condition C, is different from the previous two because it is a condition on the training data itself, not on the set of delta x values. So condition C says that there exist kappa and sigma greater than 1 and delta greater than 0, such that for all, and then there's this phrase, truncated ellipsoidal cylinders E. Okay, so we'll get to what that means in a moment. For all truncated ellipsoidal cylinders E, there exists epsilon naught greater than 0 and such that for all epsilon less than epsilon naught, the mass of objects in the expanded truncated ellipsoidal cylinder, kappa C times epsilon E, is bigger than the minimum of either delta or sigma C times the mass of epsilon E. So we mentioned that we are evaluating this doubling condition on the class of truncated ellipsoidal cylinders. What is a truncated ellipsoidal cylinder? Well, consider for yourself a two-dimensional ellipse that is filled in. It's a solid ellipse, and then we extrude that ellipse along a line to obtain an infinite cylinder that has an elliptical cross section. Next, we can truncate the cylinder by intersecting it with some half space, rotated, translated half space, creating a truncated ellipsoidal cylinder. We could even truncate it multiple times, and we would still have what we call a truncated ellipsoidal cylinder. So why do we consider this somewhat awkward class of truncated ellipsoidal cylinders? Well, the main reason is that, as stated earlier, we don't want to have to consider all possible open-bounded, even open-bounded connected domains because there's just too many of them. It's not practical to verify a condition over such a large set. But we choose truncated ellipsoidal cylinders specifically because ellipsoids are preserved by the linear transformations of the DNN, first of all, unlike rectangles or spheres. Second, the class of truncated ellipsoids is preserved in some sense under the absolute value of x. And finally, in propagating this condition through the deep neural network, we will end up using the push forward measure. And if you're familiar with the push forward measure, it deals with inverse maps. So the inverse of a linear map does not preserve ellipsoids. However, it does preserve ellipsoidal cylinders. So it may, if the linear map is singular, map an ellipsoid to an ellipsoidal cylinder. So we need all three properties: ellipses, truncated ellipses, and truncated ellipsoidal cylinders, in order to come up with a condition which rules out the undesirable properties of a data manifold, and also can be propagated through the network to the conclusion where we will verify stability. So let us compare these three conditions. First, we'll compare conditions A and B because they are similar. They're both conditions about the delta x values. So condition B is the purportedly stronger condition. And so therefore, it has two advantages over condition A. If we apply condition B at time t0, condition B leads to a stronger stability result, and that is for all times t greater than t0. Condition B also, if we impose it for all times, leads to an even better stability result, in fact, a dramatically better stability result than condition A. And condition A does not lead to improved stability at all if we apply for later times. Now, that may seem like condition B is the better condition. However, condition A does have one major advantage. It is a consequence of the doubling condition C on the training set only. So if we can verify condition C on the data set, then we get condition A for free. Then this is formalized by the following theorem. If delta x is the classification confidence map for a DNN which uses absolute value as its activation function, then if condition C holds for a training set with constants kappa C and sigma C, then condition A also holds with constants kappa A and sigma A on the set of delta x values for any parameters. So it does not matter what the parameters are. If condition C holds, then condition A holds. Note the importance of the absolute value as the activation function. The constants kappa A and sigma A in condition A will be determined via this theorem by the constants kappa C and sigma C in condition C, as well as the DNN architecture. Also, if we use condition C to obtain condition A, the constants kappa A and sigma A that we obtain are going to be worse than if we verify the condition A for any particular value of parameters. And the reason for this is that now the constants kappa A and sigma A must account for any possible parameters alpha, not just one set of parameters alpha of t0. So now we are ready to present the main stability theorem. So suppose that we have a training set T with weights nu for a DNN which satisfies either condition A or condition B at time t0, either one. Then for every epsilon greater than 0, there exists delta and eta greater than 0, such that if the good and bad sets at time t0 satisfy that the size of the good set is bigger than 1 minus delta, and the bad set is empty, then for all later times, the accuracy at time t0 is bigger than 1 minus epsilon. So this is almost exactly the notion of stability that we stated at the beginning. And more precisely, the good sets at time t greater than t0 satisfy that their size is bigger than 1 minus e to the eta star epsilon for all eta star. And here the constants delta and eta will depend on epsilon and the constants from whichever condition A or B holds. And as a comparison, we get better constants, that is a larger delta and a smaller eta, if we use condition B than if we use condition A. And that's because condition B is stronger. So as a few notes or remarks on the proofs of these two theorems, for theorem 2, that is that condition C implies condition A, The main challenge is in figuring out that what class of domains we will use to define condition C. So for that, we need to propagate condition A backwards through the deep neural network from layer to layer onto some class W of domains in Rn where the data manifold lives. And the question then is, what class of domain should we use? This class needs to be invariant with respect to the linear maps and nonlinear activations. So it needs to contain, a rather wide class of domains, but it can't be too big that the doubling condition is impossible to verify. So we settle on truncated ellipsoidal cylinders as a class that meets that criteria. For theorem 3, the proof of the problem that is multiscale in nature. So whatever estimates we use, or whatever estimates we end up with in the stability theorem, have to be compatible with the presence of many scales. So in this context, by scale, I mean the widths of the various clusters. So we may have wide clusters that do not contribute much loss because their peak is not close to beta, the minimum delta x, and narrow clusters that do contribute more loss because their peaks are close to beta. And of course, we can have many clusters in between wide and narrow. So each cluster introduces its own scale. And so conditions A and B provide a way of estimating the maximum loss contributed by clusters at every scale. And then we sum over all of these estimates to obtain an estimate for loss at time t naught, which leads to estimates for stability. The final topic that I will discuss today is the stability of bad sets and the so-called no isolated object assumption. Sorry, is there a question?
I didn't understand that.
Oh, sorry, my phone's talking to me. So the no isolated object assumption states that if we select an object from the training set, then the amount of objects that are within a distance h of that object scales like h to the theta. So this says that each class in our training set occupies a manifold of or nearly occupies a manifold of dimension greater than or equal to theta. This is a reasonable assumption. We wouldn't want to have a training set that has a lot of outliers, that is isolated objects. And it's reasonable to assume that our data manifold occupies a much lower dimensional manifold than the ambient space where the data lives. So the idea of the stability of the bad set is that we will assume that we have low initial loss, and then we will control the size of the bad set be negative eta of t for all times. So the main observation here is that the map that takes the object S to delta x of S is Lipschitz when we restrict to a single class. So therefore, if we have a single object S naught in T that is bad, that is delta x of S naught is much less than 0, then nearby objects of the same class are also bad. So if we have nearby objects, then having one bad object means that we have several bad objects. So the theorem is that we suppose that we have a training set with weights nu, and that the training set satisfies the no isolated object assumption with constants c and theta. Then for all times bigger than some initial time, the size of the bad set, or excuse me, the bad set of margin negative eta star is empty. And here eta star depends on t, and it also depends on excuse me, the Lipschitz constant of the delta x map, as well as the dimension and density of the data manifold. The idea of the proof is that if there exists a single bad element, then the Lipschitz property combined with the no isolated object assumption means that we actually have several bad objects, which means that our loss at time t is bigger than the initial loss, which leads to a contradiction because training means loss decreases. So therefore, by this contradiction, the bad set is empty. We should note that though this function that gives eta star as a function of t and various constants is a complicated one, if if we have a robust DNN, that is, if we have a small Lipschitz constant, then eta star decreases with theta, meaning that low dimensionality, eta star decreases as theta decreases. So low dimensionality of the data set turns out to be good for this bad stat stability. So this concludes my presentation. I would just want to conclude with a note that though DNNs are used widely in data science and indeed many fields, there's still a need for theoretical understanding, and there is room for analysis, mathematical analysis, to provide new information and new ideas relating to DNN algorithms. Specifically, we can study why they fail and make them more stable. We showed results on the convergence rate, showing that the loss function does converge to 0 with tight bounds, and that the parameters, though they might diverge, they diverge very slowly. We also showed analytical results, including the introduction of a new tool to study stability, delta X, the classification confidence. And we established conditions on the structure of the data and the DNN architecture, which lead to stability. That is a stability of accuracy. And in particular, we show that the flat portions of the data manifold are potential sources of instability and are ruled out via the hypotheses of the stability theorem. Finally, we employed multiscale analysis techniques to establish the properties of DNN classifiers. Thank you for your attention. Are there any questions?
So thank you, Alex, very much for this talk. If you don't mind, I've got a question. So you're talking about deep neural networks. Did you do analysis on convolutional networks for the classification problem, or on fully connected networks, or both?
So this analysis is actually applicable to any classification algorithm. DNNs are used because they are a big name, but we can and indeed, as I presented, I kind of hinted at them being fully connected with deep neural networks because they are the most easy to understand. But of course, there are many other types of DNN algorithms and other types of classifiers. This analysis works for any classifier so long as the softmax function is used in the last layer, and that we use cross-entropy loss for training.
Did you need the ReLU activation, or I know that at some point it was absolute value activation?
Right. So if we use conditions A directly or condition B to establish stability, it again does not matter that we use even a deep neural network at all, and so therefore we can use any type of activation function we want. And if we use condition C, the main tool to use condition C is this Theorem 2, which says that if we have condition C on the data set, then we can push that forward to condition A on the classification confidences. So for this theorem to hold, we must have absolute value as the activation function, or we could have another piecewise linear function. The major failing of using ReLU, I should say, we could use similar piecewise linear functions to the activation to the absolute value. The problem with using ReLU is that ReLU is an infinite to 1 function, so every negative number under ReLU gets mapped to 0. So this is a very big possible source of a small cluster. We could have a very large portion of the data manifold being mapped to 1 point, and this is not good for stability, or at least for establishing stability in this way. So currently, we do not have a theorem that allows us to use ReLU as the activation function.
But something like leaky ReLU or
leaky ReLU would be fine, because it is not one-to-one. For people who may not know what this is, I can draw on the screen here. The activation function as a function from R to R can just be graphed on the real numbers. So ReLU is flat for negative numbers, and then it is the identity for positive numbers. Leaky ReLU is almost ReLU, but not quite. It is the identity for positive numbers, but it is just a little bit less than it has a small slope for negative numbers. So since leaky value is not infinite to 1, we can use it in a similar proof to establish a different theorem similar to Theorem 2.
Okay. I see another question in the chat. So if I choose W as an open ball around a data point with radius r12, where r is the distance to the closest other data point, would this W not always violate the doubling condition?
So excellent question, Philip. I alluded to this briefly when Stefan asked about being able to use these conditions for an infinite distribution versus just a discrete distribution of data points. So I mentioned that the conditions as stated actually work much better for an infinite distribution, a continuous distribution than discrete, for precisely this reason. If I have a data point and put a small ball W around that data point and then double the size of the ball, it contains no more data points, and so it seems like I have detected a small cluster. I of course don't want every single data point to be defined as a small cluster, so I make a small change. So in the paper, you'll see versions of these conditions that account for this phenomenon by simply, if I can annotate again, simply subtracting minus m naught from the left-hand side, where m naught is the size of typically like 3 or 4 data points, so that if I have a W that contains a very small number of data points, this condition will always be satisfied. It makes the proofs a little bit more difficult to include this, and of course it makes the slides a little messier to include this. But it's not a difficult fix. Thank you.
And then there's another question. So you can prove the theorem for all one-to-one piecewise linear activation functions?
I believe so, but I haven't attempted it.
Okay. If somebody else has a question, please feel free to unmute yourself. If not, then thank you, Alex, so much for the presentation. And the next One World seminar will be next Wednesday. And the talk will be given by Franka Hoffmann on the topic Geometric Insights into Spectral Clustering by Graph Laplacian Embeddings. And see you next week, I hope.